Good morning, everyone. So in this talk, we'll be showcasing some of the work that we did actually 2 years ago, and we were too lazy to write anything about it, and then we targeted the practitioners track, although we are from academia. So in this work, what we studied was the security features of specifically the Zynq-7000 FPGA. So these are SoCs, and so these are SoCs from AMD, formerly known as Xilinx. So basically, this is a single chip with the ARM Cortex-A9 and an associated FPGA. So basically, you can write, you can boot a full Linux, you can write your own software on it, and alongside, you can use the connected FPGA to actually write Verilog and accelerate any part of your workflow that you would like to do. And ideally, like they do come with a lot of peripherals and transceivers to actually help you with real life applications, and they provide ton of benefits by putting this like CPU as well as a FPGA together. And just to highlight these, like you get flexibility both in terms of software and hardware programmability, you get good performance benefits, power efficiency, and like the topic of today is security, of course. And if I highlight some of the main applications where such devices are used, you will find them in industrial automation. You will find them a lot in medical devices, which are doing image processing, signal processing, let's say for your scans, etc. They're used in automotive, even in aerospace and defense, very widely they are used, and to an extent even in some consumer electronics. So as you can see that based on the application, many of them would require to exploit and use inbuilt security features, and like Xilinx has been working on it for many years, and they do provide some key security features on this device as well, including the other device. So one is basically the secure boot, which is enabled by an RSA 2048 authentication. They also provide other security features like immutable boot RAM, which forms the root of trust, bitstream encryption and authentication. Secure configuration, which means that you can burn in eFuse to permanently enable or disable authentication as a compulsory, let's say, workflow. It also hardens the read back feature so that you cannot simply read out any of the details, and even like you can cut out the JTAG by blowing some of the eFuses. And basically what I'll be talking about is a bug that we found in the RSA authentication part, and how we actually take it forward and try to build an exploit on top of it. So the secure boot basically of a Zynq-7000 would look typically like this. So this is something which is typically put on an SD card on the device. So if you have a physical access, you can actually read out the boot image, but part of the boot image is actually encrypted. So some of the key partitions or the key components of the secure boots are the boot ROM header. You have the partition header table, the first stage bootloader, and then the PL partition, which is the part which goes into the ARM Cortex processor, and that goes into the FPGA, which is basically a bitstream, and the PS partition, which is a standalone or a software application that goes on the ARM. Now, each of this partition can be encrypted using AES, they can be unauthenticated using HMAC, and on top of that, you can choose to activate or deactivate the RSA authentication. So you could have unencrypted partition, you can have encrypted partition, or you can have encrypted and authenticated partition. So you can individually choose which one would you want. And specifically, the RSA authentication in this device is based on RSA 2048 signature scheme. This typically uses two sets of keys. One is the primary key. Of course, like this is split into the primary public key and the secret key, and likewise the secondary key. What's the difference between them? The primary key is fixed for the device, so this is actually burned directly into the eFuse, and once it burns, it basically remains the same for lifetime of the device. To save some space, they don't burn directly the whole key, but the hash of the key. And then you have the secondary key, which is partition specific, and this can be different for each of the partitions. So for example, you can have a different key for different applications, depending on if there are multiple vendors that are collaborating to the same boot image or not. And basically it follows a two-step authentication, which is you start with the primary key that will authenticate the secondary key, and then the secondary key will authenticated partition before it executes the application. Now, if we look deeper into the boot image, what is the typical execution flow? So, you have the BIH, that is the boot index header, which contains the metadata of the boot image. Okay, it contains information like what is the encryption status of the boot image, what is the size of the boot image, and even like what is the location of the FSBL inside the boot image. And upon reset, basically boot ROM is the first piece of code that is being executed. Once executed, it will execute the FSBL, it will give command to the FSBL, and FSBL will read the PHT, that is the partition header table, and PHT will actually check the FSBL will check the PHT, find out which of the partitions are encrypted and authenticated. It will likewise either authenticate them, decrypt them, and then put them into execution. And so this is how FSBL would typically work, like just a short demo on that. Typically, like the first step is that the FSBL will authenticate the PHT before proceeding. Once it is authenticated, it will actually move to the individual partitions. So the first partition is the PL partition, which is a bitstream. So if the RSA is enabled, it will load the PL partition to the DDI memory, which will go to the PS. It is authenticated on the PS itself, and then it is downloaded to the PL part for the AES decryption. That is a hardware AES module that is on the PL part, which will actually decrypt and authenticate it, and then it will program the FPGA. Likewise, for the PL, it follows a similar process. If it will first check if authentication is required, it will authenticate it. If decryption is required, it will send it to PL for the decryption, and then the decrypted application is actually loaded on the PS. So this is the final execution of their FSBL, and once this is complete, the secure boot process is complete, and then the handover is given to the application, whatever application is running on the PS, and then depending on if you are using the PL part or not, it will communicate with the PL. Now, the threat model that we are looking into is that the attacker needs physical access to the Zynq device. Okay, we assume that you can obtain the valid secure boot image, which is quite easy because it is an external SD card and you can simply copy it, right? And the RSA authentication is actually mandatory for secure boot. So we put ourselves in this condition that the RSA fuses are burned, and therefore you cannot operate the device without authenticating it. And this is a highlight of the main vulnerability that we found over here, is that when we looked into the source code, basically what the FSBL does, it will load the PHT once, it will load it twice. Let's call it PHT1 and PHT2 just for easy naming. What it is doing is that it will authenticate PHT2, but it will use PHT1 for the secure boot process. Okay, so the FSBL authenticates PHT2, but boots with the unauthenticated PHT1, and this is like a classical talk-to vulnerability. I would actually thank the reviewers who were helping us, who told me about this particular term talk-to. I was not aware of that before. So we devise an attack on top of it. Basically, what we do is we kind of design a time shifting system where we present the PHT1 to the device. We then present PHT2 to the device, which is the genuine one and used for authentication, but the PHT1 is the tampered one, which is actually used for booting. And to do this, we had to design this small piece of wood, and basically it's an SD card switcher. The tampered and the genuine boot image are located in one of the card, and at the right point during the boot process, we switch between card 1 and card 2. So how do we validate the attack? So we have in both the SD card, we have almost similar image, but in the first one we have the tampered PHD, but in the second one we have the genuine PHD, we have the genuine boot image. Now we tried this attack it didn't work out of the box. So if I link it to the previous presentation, it turned out to be an almost vulnerability, not really a vulnerability. But what we had to do was that we had to initialize the SD card 2 in the boot process so that it can actually take the SD card. So this means we needed to add one line of code to the FSBL, which would not be possible if it is encrypted. Right. The alternate solution is that we design an SD card switcher using an FPGA and could seamlessly transit between two. But we did not go that far. Actually, we started with this process of doing it on FPGA, but we could not find any open source SD card implementation which were supporting both master and slave cards. So therefore, we could not, we did not go forward with this one. So then we asked basically the vendor, how do you feel about it? And actually, they thought that it was like it concretely demonstrates an attack. They confirmed the vulnerability. So we reported this back in March 2022, and within a couple of weeks, they actually confirmed this vulnerability, and they even released, assigned a CV as well as a design advisory was issued against this attack. And actually, when we tracked back their like the GitHub link where the FSBL is located, this vulnerability has existed in the releases from right from 2013. So it was there out for 9 long years. And this is just a showcase of the software patch that Xilinx released. Now, the next part was that can we actually use this vulnerability to enable another attack. Okay, so we look into a Starbleed attack. This was an attack which was published on Xilinx standalone FPGAs, specifically 7 series FPGAs back in USENIX 2020 by Mark Ender et al. Okay. And the vulnerability, not to go too much into detail, but just give you a brief of highlights, is basically you can take a bit stream that is loaded on the FPGA and you manipulate part of the bit stream such that instead of writing one word of the bit stream to the FPGA fabric, it will write it to this particular WB star register. Okay. And this is a warm boot register, so you can actually read back. And this is not it. It's basically when you're trying to write that piece of bit stream on the WB star register, in the process you are decrypting it. So without the knowledge of the secret key that is used to encrypt the bit stream, you are decrypting the bit stream and you are recovering one word of that. And then you can loop on the bit stream to actually recover the whole bit stream 32 bits at a time. So this is how it looks. You make a Starbleed bit stream basically, which will go to the FPGA. It will try to program the fabric apart from one word that is decrypted, and instead of being written in the fabric, it is loaded on the WB star, and then you can simply read it back. Now, this attack was shown on 7 series FPGAs, and typically an RSA authentication would disable this attack or prevent this attack. So we wanted to test, is it possible to use the vulnerability that I just presented to actually take forward this attack to even work on Zynq-7000 devices. So the key challenges were bypassing the RSA authentication, which we actually did using the previous vulnerability. How do we build a secure boot image without knowing the key? So this is typically the same process that we do. So the part that we are tampering is actually the unencrypted part. So it does not bother us. So we can directly copy the encrypted part into our main image. But the main challenges over here are the read back part. So in other words, when we tried the Starbleed attack, even taking this vulnerability into the account, it did not work out of the box on Zynq-7000 devices. So we had to adapt it, and there were several challenges. First of all, when we are talking between PS and PL, a bad bit stream will actually not will not enable the PL on a secure boot process, and therefore we cannot use it. And we absolutely require that the PL part is perfectly initialized, and so in other words, there is the done pin that should be turned on so that the PCAP can be activated and it can read back. Otherwise, we cannot activate the PTAG. We could do it using the JTAG, but we kind of assume that JTAG will be disabled in a real device. So we do not, we tested it, it works, but we do not take this like as a valid attack. So we wanted to see if we can actually use the PCAP to recover the bitstream. There are more details in the paper, but how do we basically do it is that like the small trick that actually worked over here is that we configure the PL first with a valid bitstream. So there is a part of the bitstream that is valid. What it will do is that it will actually go to the PL and it will initialize it. It will put the done pin to 1, and thereafter, without initializing the PL, which is a not recommended practice, we actually send the Starbleed bitstream. And once we do that, it actually fails because it's an invalid bitstream. But what it does is like it will write that particular bit of that particular 32 bits of the bitstream decrypted into the WP star register, and then we can actually simply copy it back to the PS and read it out. But this puts the device into a non-responsive state. So this means like for every 32 bits like recovery, we need to power on the device. So therefore, like although it's an offline attack, so we can do it over a couple of days, but like we need one full power on to recover 32 bits at a time. So I'll conclude this like with a short demo over here. Okay. So here we have the authenticated boot image. So what we'll be showing is like in the first step that okay, everything works, the secure boot is working. So we are now booting the victim image. So when you see the log, basically the image is actually successfully booted. So this part was set up. Now we show that either tampering the PHT in the first step, and the second part is like tampering the partition will actually fail it. So just to assess that the secure boot is actually perfectly aligned. So we are booting using the SD card 1. So here we have a tampered PHT. And basically this results in authentication failure, and therefore the secure boot doesn't work. We also try the other SD card individually where there's a tampered partition. And not to surprise, actually, you'll see that this will also fail. And then we use our SD card switcher to actually try to enable this vulnerability. All right. So here we are using the SD card switcher. For the demonstration purposes, we added like a visible delay between the switching, but this was just flipping a bit, so we could automate it easily. And therefore, we have a successfully booted application And this application is actually the Starbleed attack. So like here we show that we are able to recover 32 bits of the bitstream which is decrypted. So with this, I come to the conclusion. So we identified a critical security flaw in the Zynq-7000 FSBL, which was due to mishandling of the PHT data. We validated it using the SD card switcher, and we even exploited to enable the Starbleed attack on Zynq-7000 devices. And this was a vulnerability that was there in the FSBL code for over 9 years, since 2013. This was acknowledged by the vendor. CVE and a design advisory was issued, and a software patch was promptly released for the FSBL. We checked the patched version, and we did not find the same vulnerability there. We also went forward and we checked the boot ROM code using the traffic analysis, and just to see if there's double fetch vulnerability or the talk to vulnerabilities in the boot ROM code as well. But we verified that the boot ROM code does not have this. So that was a good news. And with this, yeah, thank you. And yeah, a special note to my colleagues who did the heavy lifting here, Prasanna and Arpan. Especially Prasanna, I think you saw the fingerprints in the demo video.
All right, let's thank the speaker.